All right, let's talk about the chemistry of water. Water is one of the most important molecules to life on Earth. It's hard for us to imagine how life would exist on another planet without water. Water is the solvent of all the chemical reactions that occur. Everything in your cells is dissolved in water. Your DNA is dissolved in water. All of the reactions that are necessary for life occur in this watery aqueous media inside cells and outside cells. One of the reasons why water is such an ideal solvent is because of its polarity. Oxygen as an atom, the element oxygen, is what we call electronegative. In fact, it's one of the most electronegative things in the periodic table. And that means that it tends to draw that electron cloud to itself. So those electrons, remember, are buzzing around the nucleus in an electron cloud. Oxygen, if it's one of the atoms in a molecule, will draw the electrons to itself, and the electrons will spend more time buzzing around the oxygen than around the other atoms that are not electronegative. So in a water molecule, we have an oxygen and two hydrogens, and it's asymmetrical. So, and this is due to the exact orbitals of those outer valence electrons, which we're not going to worry about too much, but that's the reason why this molecule is asymmetrical. So the oxygen is hogging the electrons, and the hydrogens then have the electrons spend less time around the hydrogen. So that means that the oxygen gets a partial negative charge and the hydrogens have a partial positive charge. And this little symbol here, this little squiggle, that's a lowercase delta, the Greek letter delta. And you've probably seen an uppercase delta that looks like a triangle. We use that in science to stand for the word change. Like if you see delta T, that's either change in temperature or change in time. Lowercase delta means partial or less than 1. So this negative here with the little delta in front of it, that tells us that it's a negative charge, but it's less than 1. So an electron has a negative charge of -1. So it's less than that. And the same with these positive charges here. So it's positive, but it's not a +1 charge, which is the same as 1 proton. So it's less than that, because there are still electrons around the hydrogen nucleus, just not very much. And so what this creates, so these bonds are polar covalent bonds. They're polar. We're using the word pole the same way as you use it in a magnet. So if you remember those magnets that you used in grade school that had a plus on one end and a minus on the other end, there are poles, and the two positive poles of two different magnets repel each other. But if you put the positive and the negative poles together, then they attract. And this, we're using the word pole in the same sense. So a water molecule has a negative pole and a positive pole. And it will attract this negative oxygen is going to attract things that are positively charged, and these positively charged hydrogens are going to attract things that are negatively charged to them. And that's really what gives water all of its special properties. So we call this attraction a hydrogen bond. So to have a hydrogen bond, you need a positively charged hydrogen, which you're going to get that when you have it bound to something electronegative like an oxygen. This hydrogen will be positively charged, and then if you have anything else nearby that has a partial or a full negative charge, it's going to be attracted to that positive charge. That's a hydrogen bond. Ammonia is electronegative as well, like oxygen. It's not quite as electronegative as oxygen, but it still will, when it's bound to hydrogen, like in an ammonia molecule, it's going to have a partial negative charge as well. And this is one of the ways that we can tell what's going to dissolve in water and what is not going to dissolve in water, like oil. And we'll talk about the difference between hydrophilic and hydrophobic as well. That's also important. in biology. So water being polar, that also means that water molecules are attracted to each other. So in water, we have all of these positively charged hydrogens being attracted to the negatively charged oxygens on another molecule. Now this hydrogen bond, which is represented by the dotted lines here, this is a weaker bond than ionic bonds or covalent bonds. It's weaker. But when you have this kind of a bond between all of the molecules in a solution, it's going to change the properties of that solution. So even though a hydrogen bond is a relatively weak bond, it's going to create some special conditions and special properties that water has. And we are so used to these special properties of water, we take them for granted. We don't even really notice how weird these properties are that this liquid has. So let's talk about what those are. So one of the things that we can talk about in relation to water is whether another molecule is going to dissolve in water or not. So if it's going to dissolve in water, then we call it hydrophilic. So philo is Greek for love, hydro is Greek for water. So hydrophilic means water loving. So things that dissolve in water, we say they're hydrophilic. If it doesn't dissolve in water, like oil, then we say it's hydrophobic. Phobic is hate. So hydrophobic is things that hate water, like oil. They don't dissolve in water. So we can talk about a molecule that being hydrophilic or hydrophobic. And there's things in between. There are molecules that are somewhat hydrophilic and somewhat hydrophobic, or part of the molecule is hydrophilic, part of it is hydrophobic, you know, because nothing is simple in biology. And many times, if we just look at a molecule and we see other oxygens bound to hydrogens, like this would be some kind of an organic alcohol here with our oxygen group on here. This oxygen is going to have a partial negative. This hydrogen is going to have a partial positive. It's going to hydrogen bond to the water, so it's going to dissolve. It's going to be hydrophilic. So if you're trying to determine if something is hydrophilic or hydrophobic, if I give you a molecular structure, you want to look for polar covalent bonds. So if the molecule has nitrogens in it, if it has phosphorus in it or phosphates, or it has sulfur even, is a little bit hydrophilic, then we know that there's going to be partial charges building up. And that's going to indicate that this molecule probably is going to dissolve in water. Something like sugar has a lot of oxygens in it. So that's the reason why sugar dissolves in water. Sometimes the molecules even have a full positive or negative charge, not even a partial charge. It has a full positive or negative charge. It's some kind of an ion. Those also are going to be able to hydrogen bond with water. Hydrophobic molecules have mostly nonpolar covalent bonds and no charges. And these things tend not to dissolve in water. So oils, fatty acids, these are hydrophobic because almost the entire molecule has none of these polar bonds, and very few or no electronegative elements like oxygen, nitrogen, sulfur. So one question where hydrophilic versus hydrophobic becomes of interest is when we're talking about vaping, because the inside of your lung is wet and hydrophilic. And so things that dissolve in water can enter your bloodstream by dissolving in that wet layer on the inside of our lungs. Oils can damage our lungs because they are not, because they are coating this hydrophilic wet inner layer on our lungs. And that's one of the theories behind what is happening with vaping THC versus nicotine. You probably know you can buy lots of vaping fluids that have nicotine in them. So here is the nicotine molecule, and you can see that even though it's mostly just carbons and hydrogen, so it has a lot of hydrophobic characteristics, because of this nitrogen and this nitrogen, nicotine in fact will build up enough partial negative charges to be able to dissolve in water. So nicotine is just hydrophilic enough that it can dissolve in water. So when they develop nicotine-containing vape fluids, it's usually a water-based fluid. Now, THC, on the other hand, which is one of the active ingredients in cannabis, is extremely hydrophobic. Even though it has 2 oxygens here, there's a lot more carbons. Every place you see a little kink in this chain or in this ring, that's a carbon. And there's a lot of hydrogens on there too that we just leave out for convenience. So THC is very hydrophobic and it has to be dissolved in oil. So this is what doctors right now are hypothesizing is the reason why people who are vaping THC containing products are having these lung problems. And it could be either that the oil itself is damaging the lungs directly because inhaling oil into your lungs is bad, or that heating the oil is producing formaldehyde, which is toxic to the cells in your lungs. So either way, if you vape, you might want to check whether the vape fluid is oil-based fluid, in which case you should probably avoid it, or if it's a water-based fluid, in which case it's probably safer than an oil-based one. But you will not find at this time a water-based vaping fluid that contains THC. They're all oil-based, although people are working on that because this is obviously not working. And it doesn't matter what kind of oil it is. They're generally using oils that are edible, like soybean oil. It's completely different, though, if you swallow it versus if you heat it up, vaporize it, and inhale it. That appears to be the problem. So what are the special properties of water due to these hydrogen bonds? There are 4 special properties of water, and we'll talk about each of these. One is the high heat capacity and boiling point. So heat capacity is the fact that water can absorb a lot of heat and not change temperature that much compared to other liquids. And the boiling point for water is really high. Water is a pretty low molecular weight molecule. It only has a molecular weight of 18, which is pretty low. And it has an extremely high boiling point for something with such a low molecular weight, and that's due to the hydrogen bonding. The fact that ice floats, this is something we just so take for granted with water, but pretty much any other substance you can think of, the gas is the least dense, the liquid is more dense, and then the solid is the most dense. So for almost any substance you can think of, if you freeze it, the frozen version will sink to the bottom of the liquid version. But for ice, that's not true. The liquid is the densest version of water, and that's weird. Cohesion and surface tension. This seems like the most obvious one to be the result of hydrogen bonding because those water molecules are sticking together with the positive and negative charges attracting each other. That means that water sticks to itself, and this creates surface tension, and it also creates capillary action, which we'll talk about those. Water, because it's very polar, is also a good dissolver of salts, and this is really important for cells because every living cell on Earth has dissolved salts like sodium, magnesium, and calcium, and potassium, etc. So water's very high heat capacity is the reason that it's the reason that water seems to take so long to boil when you heat it up, and it's also the reason that when you sweat and your sweat evaporates, it's very cooling. So if we look at this little graph here, so on the y-axis here is the amount of heat being put in. So more and more and more heat being added to the system. And on the x-axis here is the temperature in Celsius. So freezing is at 0 Celsius, boiling is at 100 Celsius. So as we heat up our ice, because of course if it's below 0, it's frozen, we heat it up. When it gets to 0, it continues to absorb heat, but doesn't change state yet because hydrogen bonds are breaking. Then when it becomes a liquid, we still have hydrogen bonds, but now in a liquid water, the molecules are constantly rolling and moving around past each other. So in liquid water, the bonds are breaking and reforming, breaking and reforming. So we're adding heat, we add heat, it heats up, heats up, heats up, and then you get to 100 degrees. That's the boiling temperature of water at sea level. And then you keep adding heat and it doesn't boil, and you keep adding heat and it's still not boiling, and you keep adding heat and it's still not boiling, and then finally it starts to boil. So the old saying, a watched pot never boils, is a reflection of the fact that you can have water that's just about to boil and you have to keep adding an enormous amount of heat after that point to continue to get it to boil. And this is what happens when you sweat and your sweat evaporates. It takes this enormous amount of heat with it when it leaves your skin. And the reverse happens as well. This is why steam burns are so dangerous and damaging, because steam, when it hits your skin, cools down and turns into a liquid and releases all that heat. Water's high heat capacity also affects the temperature of the air. This is a really important factor in climate modeling. The computer models that are trying to predict temperature changes around the world have to take this into effect. So if you've ever been to LA, if you go inland, like there's a little ridge of hills right here that you have to drive over, and Riverside is on the other side of the hills. I'm not going to call them mountains. They're not that big, but they're not little either. If you're out here in the desert, out in San Bernardino, it can be very, very hot. You start driving in, and then you hit these little hills, and you drive over the hills, drive over the hills. You get to the other side of the hill, and it could be 20 degrees lower in temperature. You keep going, you keep going, you get down to the beach, and now you need a sweatshirt because it's too cold. And the same thing happens in Seattle. Even Lake Michigan moderates our temperature in Chicago. Chicago has cooler summer temperatures and warmer winter temperatures than cities. If you go just 100 miles away or even 50 miles away, like to Rockford, Illinois, which doesn't have, it's not as close to Lake Michigan. It's hotter in the summer and it's colder in the winter. Seattle is further north than Chicago. It's about as far north as Green Bay, Wisconsin, but it hardly ever snows there. If it does snow in the winter, it tends to melt right away. And in the summer, it hardly ever goes above 80 degrees. Nobody has air conditioning. Nobody's house has air conditioning. I lived in Seattle for 5 years, and no house has air conditioning in Seattle because you don't need it. People hardly even have fans. Nobody has fans in their house because you don't need it. It just doesn't get that hot. And in the winter, it's the reverse effect, and that's because the Pacific Ocean is so nearby. And the weather tends to come off the Pacific onto land. So that really moderates the temperature. Another property of water, again, is the fact that ice floats. And this has had a big impact on the evolution of life on Earth. Imagine what would happen if ice was more dense than liquid water. As soon as ice froze on the surface of a lake or a pond or the ocean, it would sink. And then more would freeze, and then that would sink, and more would freeze, and then that would sink. And the ponds and lakes would freeze from the bottom up, and there would be no way for fish or other organisms to survive below the ice during the time when it's cold. So this is a huge impact on life. So the reason that liquid water is denser than solid water or ice is because of what happens to the hydrogen bonds. When you freeze water, it crystallizes, and the hydrogen bonds all line up and form these little crystal lattice structures that actually pushes those water molecules just a little bit further apart. So it's the hydrogen bonding again that is the reason that ice floats. The cohesiveness of water allows plants to grow tall. It's the capillary action. The water evaporating from the leaves allows more water to be drawn up in the vascular tissue of the plant. The cohesiveness of water even helps our blood to move through the narrowest blood vessels in our body, the capillaries. Surface tension is related to this. It's considered part of the same cohesiveness property. There are many organisms that use the surface tension of water either to walk on the surface like this spider, or to grab bubbles of air and drag them below the surface. There are a surprising number of spiders, insects, and sea animals that use bubbles and the fact that water has a high surface tension in order to either increase their buoyancy and float on the surface, or because they're air breathing to bring their own supply of air under the surface of the water. Water is very polar and can dissolve salts. Every cell on Earth is full of dissolved salts, and the ocean is full of dissolved salts. All cells are surrounded by water that also has dissolved salts in it. So, and it does this because salts are ionically bonded, like sodium chloride. There's a positively charged ion and a negatively charged ion, and when you put them in water, the ions separate and those ionic bonds break. And the positively charged ions, like the sodiums, will bond with these partial negative charges on the oxygen, and the negatively charged ions, like the chloride, will bond to the positively charged hydrogens on the water. Water can also dissolve really large molecules as long as they have a lot of oxygens or nitrogens that allow them to be hydrophilic. So even your DNA molecules, which are gigantic and can contain billions of individual atoms, are completely hydrophilic and dissolve in water because they contain a lot of oxygens. Most proteins in your body, like collagen, are completely hydrophilic because of that as well. So most of the molecules that living cells make are large molecules that are hydrophilic because they have a lot of nitrogens, oxygens, or sulfur that allows hydrogen bonding. pH is a property of water, and we always write it this way: lowercase p, uppercase H. Even if it's in a title, we write it that way because the P stands for a mathematical function and the H is for hydrogen. It's the atomic symbol of hydrogen, so it's always a capital H. So a solution that is not watery, like oil, cannot have a pH. pH is a property of water. So if you don't have any water in whatever liquid you're talking about, like liquid methane or motor oil, it doesn't have a pH. It refers to the amount of free hydrogen ions in a specific solution. So water itself tends to dissociate into free hydrogen ions and hydroxide ions. So remember, water is H2O. So one of those H's tends to get lost and leave behind a hydroxide ion. But then they will stick together again as well. Well, if you have more hydrogen ions than hydroxide ions, that solution is an acid. If you have, or it's acidic. If you have excess hydroxide ions, then the solution is basic. Now we know that really those free hydrogen ions are not going to be, they're not going to stay free, they're going to stick to other water molecules. They stick to that negatively charged oxygen and make this hydronium ion, which is H3O+, but that just makes it more complicated than we need it to be. So here's water, pure water. If we have pure water, almost all of it, over 99% of the molecules, are going to be in the form of H2O, but a small percentage of them, the water will lose, one of the water molecules will lose a hydrogen to another water molecule, and we will have a very small percentage of the water that will be hydroxide ions and hydronium ions. Now in pure water, these will be equal. We'll have the same amount of hydroxide and hydronium ions. And you'll notice the double-headed arrow here, that means this reaction is going in both directions. It's a state of equilibrium. These molecules are sticking back together and new water molecules are dissociating. Our pH scale goes from 0 to 14. You might have seen an older pH scale that only goes from 1 to 10. We don't use that one anymore because this number 0 to 14 actually is more related to the mathematical function that we're using here for pH. So pH, if a pH is low, that means there's a high concentration of free hydrogen ions. So, and this here, these numbers on the left, these are the actual concentration of hydrogen ions. So and it's because it's a negative exponent, that means the higher the number, the lower the concentration. So 10 to the minus 14th is a decimal with 14 zeros and then a 1. So that's a really tiny, tiny, tiny number. 10 to the minus 1 is just 0.1. So that is a relatively large number. So this exponent is just, so that's why these exponents seem to be the reverse of the pH numbers. So a pH of 1 or 2 is a really high amount of excess hydrogen ions. If we have a pH of 13 or 14, that means we have a really low amount of hydrogen ions. Pure water, the hydrogen and hydroxide ions are going to be equal. Pure water is going to be a pH of 7. Your cells in your body, most living cells in fact, are a pH really close to 7 inside the cell and outside the cell. Your blood is outside your cells. It's also really close to pH of 7. You'll notice that there's a lot of foods here listed in the acidic range. We tend to like things that are a little bit acidic. We add acids to our foods to make them taste better, like vinegar and lemon juice. Coffee and tea are both very acidic. Most fruits are somewhat acidic, and they tend to be things that we like. Now, if you look in the alkaline side here, you see a lot of things that don't taste good. Baking soda, soap, detergent. In fact, things that are alkaline tend to taste bitter, soapy, unpleasant. Seawater, if you ever tasted seawater, it's a little bit alkaline. And why is that? Why do we tend to like things that are acidic and we tend to not like things that are alkaline? And there's a few exceptions to that, like chocolate is a bit alkaline, but if you've ever tasted 100% pure chocolate, it's very bitter. We usually don't eat it 100% pure. Most people don't anyway. And we think that there's an evolutionary reason for this, that plant poisons also tend to be alkaline. So the early humans who, especially kids, you know, if you've ever taken a toddler outdoors for a walk, they put everything in their mouth. The humans who liked alkaline or didn't taste it as bitter, they didn't survive to pass their genes on to the next generation because plant poisons tend to be alkaline as well. So acids are less likely to be toxic in the plant world. So acids and bases affect this hydrogen ion concentration. So things that are acidic tend to increase the hydrogen ion concentration, like hydrochloric acid dissociates and increases the concentration of hydrogen ions. Bases absorb or reduce the hydrogen ions in a solution, like ammonia absorbs hydrogen ions. Sodium hydroxide is a salt. The sodium ions bind to, or the hydroxide ions bind to the hydrogen ions and remove them from the solution. We use the pH of our blood to trigger breathing and to indirectly monitor the amount of carbon dioxide in our blood. Our blood is extremely tightly monitored for pH. We often think that what we're sensing is oxygen levels, and we do sense oxygen levels. So there are sensors in our blood vessels that detect oxygen, and there are different sensors that detect pH. Now, oxygen does not affect pH. How much oxygen is in your blood has no effect on the pH of your blood. Oxygen is not acidic or basic. It's neutral. So we do detect the amount of oxygen, but it does not trigger the urge to breathe. You know, when you hold your breath, after 15 or 20 seconds, you start to get the urge to breathe. It's not because of low oxygen. Low oxygen increases your heart rate. It does not trigger the urge to breathe. The pH sensors that sense a pH change, that's what triggers the urge to breathe. So what happens when you hold your breath? Hold your breath, you're not exhaling CO2 anymore. The amount of CO2 in your blood starts to go up. Oxygen is going down, but that's not affecting pH. CO2 is a weak acid. CO2 dissolves in water and produces carbonic acid. So as you hold your breath, your blood starts to become more acidic. The pH starts to drop because the amount of CO2 in your blood increases. This pH sensor detects that change in pH, and it's a very slight one. It's a very slight change in pH. That sends a signal to your brain to breathe, and eventually that urge becomes irresistible. And this will happen even if you're unconscious, even if you're asleep. This will still happen. This sensor will trigger the breathing center in your brain and trigger you to breathe. What can happen is that when your CO2 is going up, oxygen is going down because it's being used by your brain and your tissues. If you deliberately mess with the system, like by hyperventilating, so you can hold your breath longer. So a lot of people know this when they're, you're in a pool. If you hyperventilate and then you hold your breath, you can hold your breath longer. Why? Because you're blowing off excess CO2. Unfortunately, your oxygen level remains exactly the same. So when you hyperventilate, you decrease your CO2, but you don't increase oxygen. That's the same. Now you hold your breath. So you're holding your breath, CO2 is going up, oxygen is going down, but we're not sensing, the oxygen is not triggering us to breathe. So you can actually lose consciousness from lack of oxygen before the CO2 system gives you that irresistible urge to breathe. And this is the unfortunate cause of many accidents every year where experienced swimmers drown because they hyperventilate, they artificially lower their CO2, their oxygen is still the same, and then while they're holding their breath, oxygen goes down. They lose consciousness, but their CO2 level has not increased enough yet to trigger the urge to breathe. So if you want to experiment with this, do it on the couch, not in a pool. And if you're swimming, trying to hold your breath for a long time, don't hyperventilate. It works, but it's not safe. There has been a lot of stuff in the pseudoscience world lately about alkalizing your body, and we want an alkaline diet, and we're going to alkalize our blood to prevent cancer or something. That you have to eat foods on the alkaline foods list, which are mostly fruits and vegetables. And that will make you healthier because it's going to change the pH of your blood and tissues. And cancer cells tend to be acidic, so we're going to alkalize, and that's going to prevent cancer. We'll talk more about why cancer cells have acidic surrounding tissues when we get to talking about cancer later in the semester. The reality is, though, your blood and your cells as well, the pH is really tightly controlled. Between 7.35 and 7.45. If it goes down just a tiny bit, that triggers breathlessness. And it doesn't change based on your diet. You could eat 100% meat for a week and we'll measure your blood pH, and then you could switch and eat 100% plants for another week and it would be exactly the same. You cannot affect your blood pH by your diet. There's no evidence that eating the so-called alkalizing diet has any health benefits whatsoever, or whether you actually change the pH of your body in any way. If you could alkalize your blood, it would be a medical emergency. There are medical conditions associated with having slightly too acidic blood as well as slightly too alkaline blood. These are medical emergencies that are the result of various systems in the body, including the kidneys, having a massive life-threatening problem. So don't base your diet on pH, because it's not based on science. So in this section, we talked about ionic bonds and covalent bonds, with covalent bonds being the stronger bonds in biology. Covalent bonds are shared electrons. Within covalent bonds, we have polar covalent bonds, and these usually involve a hydrogen bonded to oxygen, nitrogen, or sulfur. Non-polar covalent bonds in biology are usually between a carbon and a hydrogen, and they share the electrons equally. So if you see a molecule that's mostly made of carbons and hydrogens, it's going to be hydrophobic, like oils. It's not going to dissolve in water. Water has special properties, 4 special properties, which are its high heat capacity, its cohesiveness, the fact that ice floats, and the fact that water is a polar solvent. pH is a measurement of an aqueous solution. If something has no water, it cannot have a pH. And we are measuring the free hydrogen ions. So the more hydrogen ions there are, the lower the pH is. So a pH of 2 would have a lot of free hydrogen ions in it. Acids are pH below 7, bases are things that are above 7. And water, 100% pure water, is a pH of 7, exactly neutral. In the next section, we're going to talk a little bit about some basic biochemistry. We'll talk about what proteins, fats, carbohydrates are, and a little bit about DNA and RNA.